Hi team, how you going? It's Justin here from zstatistics.com, giving you a video today on the goodness of fit test, which is one of a couple of chi-squared tests that I deal with on zstatistics.com. Now, I do have a video on the chi-squared distribution, which tells you about the history of the distribution and how we derive it. So you can delve into that if you like, but that's not necessarily required. If you're just after the goodness of fit test, you've come to the right place. So let's jump straight into it, shall we? Now, as I said, there's a couple of chi-squared tests hanging around, and they all tend to do the same kind of thing. They test a theoretical categorical distribution versus an observed categorical distribution. So a very simple example of that might be to say, well, let's consider the three different, main eye colors for simplicity: blue, green, and brown. Now, someone might have the theory that in a particular population, the prevalence of each of these eye colors is a third, and a third. Now, that's a theoretical categorical distribution. Now, of course, you could get some kind of sample, which you could use then to test whether the theory is up to scratch. And to do that, you would use a chi-squared test. In this particular example, you'd be using a goodness of fit test. Of course, we're testing how good the fit is of the theory to the actuality. Now, you can also do a chi-squared test for independence, which I've got in a separate video, but keep in mind, it's actually going to be very similar. It's the same kind of idea, and I'll deal with that more in that particular video, but just keep in mind that this chi-squared stuff is always going to be looking at a theoretical distribution versus an observed distribution, particularly when dealing with categorical data like this. Okay, so let's have a look at the goodness of fit test. In this particular video, I'm going to give you two different worked examples of the goodness of fit test. I'm also going to show you the formal testing procedure, which will include me looking at the decision rule method and also the p-value method as well. So that's going to be good for you just from a hypothesis testing perspective. But importantly, I'll also be doing some calculations using some Excel formula. So those pesky statistical formula they use in Excel, I'll be able to show you how to use that, which will be helpful. And I'll also be using some statistical tables as well, just for those people who are at uni where they still require you to use tables. I'll just make sure I cover that off. And the most interesting part of this video, I think personally, is where I deal with this question: where is the normal distribution hiding? I've not seen many other videos deal with this, but just to summarize very quickly, the chi-square distribution is derived from a normal distribution. So the question I'm going to answer, hopefully, is that where in this delicious looking formula that we use for our chi-squared tests, where is the normal distribution hiding? And in answering that question, I'm actually also going to be proving that this formula works. So it's a real 2-for-1 play as well. Anyway, so that is what is coming up. So shall we get into it for real? Let's do it. So here is my first example of a goodness of fit test. It's a very simple one. I'm saying that in an art class of 75 students, 11 students are left-handed. And my question is, does this class fit the prevailing theory that 12% of people are left-handed? Now, if you've come to this video having done a few examples, you might want to pause the video and just give this a go yourself and then see if we get the same answer. But if this is new to you, let's just keep kicking on. The first thing we might need to do is calculate the expected number of students out of the 75 that would be left-handed. Now, if we presume this 12% is correct, 12% of 75 happens to be 9 exactly. But what we can do is we can construct for ourselves a table that might look a bit like this. Left-handed, right-handed, we've got 11 and 64 in the observed column. That's what that O stands for, observed, with a total of 75. And we can compare that to our expected number of left-handed and right-handed people in the sample, which is 9 and 66 respectively. So the question is going to be, how close is our observed sample to what we might expect? Is our observed sample far enough away from what we expected to really cast some doubt on this prevailing theory. That, my friends, is a goodness of fit test. Now, all that's left to do is actually do all the calculations. So shall we? Now, in a formal goodness of fit test, we need a null and alternate hypothesis. So our null hypothesis is going to be that the expected distribution holds, or the prevailing theory indeed holds. So 12% of people are left-handed. And we're going to see if there's enough evidence to reject that. So our alternate hypothesis is that the prevailing theory is incorrect. In other words, if we were to write this statistically, pi, which is the population proportion, is equal to 12% or 0.12. That's going to be our null hypothesis. And our alternate hypothesis is that some other proportion aside from 0.12 is in fact the true proportion. Now, for any goodness of fit test, we're going to need a level of significance, which is going to be 5%. And if hypothesis testing is new to you, I'd suggest watching my very first video on hypothesis testing, which gives you a good intuition behind the process of hypothesis testing. So I'll put a link up to that now, but I presume if you're watching this video, hopefully you've had some experience with hypothesis testing. So here we go. I've just rearranged things a little bit. There's our null hypothesis, our alternative hypothesis, and our level of significance. So we need to consider our test statistic. Now, because it's a chi-squared test, we know it happens to be that. The test statistic looks a bit like this. It's the observed minus the expected value of each category, all squared, then divided by the expected value. And then we sum that up across all of the particular categories that we have in our sample. So this is going to be a chi-squared distribution. But if you recall from the previous video on chi-squared distributions, you'll know that we need a degrees of freedom associated with this chi-squared distribution. And here the degrees of freedom is going to be 1. Now the reason why it's 1 degree of freedom is this. If you consider your observed distribution here, we have 11 people that are left-handed. Out of 75 people, we already know how many people are going to be right-handed. It's just going to be a simple subtraction. So realistically, there's only one piece of information in this observed sample. As soon as we know 11 people are left-handed, that's it. That's all we need to know. And we have the number of right-handed people as well. It's like if I told you that 60% of the people that view my videos are female, you don't need me to tell you that 40% are male. There's only one piece of information there, really. So a way to get the number of degrees of freedom is just finding the number of categories and subtracting 1. So you might see degrees of freedom equals k minus 1. That's often quoted in places. But it's just the number of categories minus 1. Now there is one condition we actually need to check before we move on here. I've said this is a chi-squared distribution with 1 degree of freedom, but we need to make sure that the expected frequencies are all greater than 5. Now the reason being is not so obvious, but it has something to do with that normal distribution that's hiding. And I'll get into that in the next section. But for the moment, let's just presume that it's when the expected values are greater than 5, our equation here is going to be distributed like a chi-squared distribution. If the frequencies were less than 5, we wouldn't be able to use this formula, or certainly wouldn't be able to use the distribution to solve the problem. But let's move on. So we can then use this knowing that there's 1 degree of freedom. So I've put here that little subscript 1 now to show that there's 1 degree of freedom. And we can use this formula where we take each of the observed values, subtract the expected value, and then square it. So 11 minus 9, all squared, divided by the expected value, which is 9. And then we add to that the 64 minus 66 all squared, divided by the expected value of right-handed people in the sample, which is 66. So hopefully you can see what's going to happen with this test statistic. If the observed distribution looks very much like the expected distribution, if they're very similar, this chi-squared statistic is going to be very low, going to be close to 0. So this chi-squared stat gets bigger when the observed distribution moves further away from the expected distribution. That's important to remember. So we can calculate this pretty easily and we get 0.505. All right, so what's our decision rule? How do we then decide whether this chi-squared value is extreme enough to reject the null hypothesis? we need to consider the shape of the chi-squared distribution, which looks a bit like this when we have 1 degree of freedom. Now, for a hypothesis test, what we usually do is we say, if our test statistic is in the most extreme 5% of the distribution, we will say it's in the rejection region, and we will therefore reject the null hypothesis. So how do we find this critical value beyond which we're going to reject? Well, that's where the Excel formulae are going to really help you out. So you can see here, if you use the equals chi-squared.inv formula, that provides you a value of the chi-squared distribution, a point on the chi-squared distribution for a given probability. Now you can see there are 2 arguments to this formula. I have to put in the probability first, which happens to be 0.95. It's not 0.05 like a 5% level of significance. It's actually 0.95 because the way this formula works is that it always expects the probability to the left of a particular value. So if we want this particular point here, above which lies 5%, we must know that below that value lies 95%. So we can use these Excel formula to find this particular value of chi-squared on this distribution where there's 5% in the upper tail, or in other words, 95% in the lower tail, if you call it that. Now, this second argument is in fact the degrees of freedom. So this will actually give you a different answer depending on the number of degrees of freedom, because of course, the distribution actually changes for a given degree of freedom. So if you plug that into your version of Excel, you'll find you get 3.841. So that means that this point here is 3.841. So that means if our chi-squared statistic is greater than 3.841, we'll reject the null hypothesis. Now, if you wanted to do this old school and you were using tables instead, so say you're at university and this is all you've got, then it's pretty simple. You just look down for your degrees of freedom here on the side. Of course, in this case, it's just 1 degree of freedom, so we're on the top row. And here it says the probability of a larger value of chi-squared, of course, that's going to be 0.05 because there's 5% in the upper tail. So 3.84 is our number. So you can use tables if that's all you got. Of course, if it was a 1% level of significance or a 10% level of significance, you'd be using these numbers either side. But here it's the 5%. So going back to our conclusion, in this case, unfortunately, we could not reject the null hypothesis because our chi-squared statistic is not greater than 3.841. So the final statement we make here is to say that there's not enough evidence to suggest the proportion of left-handedness is other than 0.12. Ooh, that's an interesting conclusion. Seems like I'm using a double negative. There's not enough evidence to suggest the proportion of left-handedness is other than 0.12. And that's really the best way of concluding here, because all we've been able to show is that there's not enough evidence to get us to this alternate hypothesis. Okay, that's not to say that the true proportion is in fact 12% or 0.12. We just haven't got the evidence to reject it. So yes, you could loosely say that this fits the prevailing theory that 12% of people are left-handed. But I guess more strictly, you could probably only say that we don't have the evidence to reject the prevailing theory. Again, if you want to convince yourself of that, just think about what happens when someone is on trial for murder. When they get found not guilty, does that necessarily mean they're innocent of the crime? No, it doesn't. It just means there's not been enough evidence to convict them of that crime. So that's the analogy you can kind of create here if you're not satisfied for my conclusion. All right, so there's actually another way we can deal with this. And as I said in the beginning of this video, I want to look at the p-value approach as well. If we have a look again at this distribution, we know that 0.505 is the calculated value of chi-squared, which exists somewhere here. There's 0.505 on the distribution. And we know we're going to be rejecting the null hypothesis if this 0.505 happens to be in the tiny tail up on the positive side of the distribution, which clearly you can see here it's not going to be. But how would we do this formally? Well, we could construct what's called a p-value, which is basically like the area in the upper tail above that particular point. So the p-value is going to be this shaded region here, and you can calculate that using Excel as well. And you'd use this formula here, which is the chi-squared dot dist formula. Now the chi-squared dot inv formula gives you a chi-squared value for a given probability. Chi-squared dist gives you a probability for a given chi-squared value. Okay, so if we subbed in this chi-squared value of 0.505 and we told it, yes, we want 1 degree of freedom, please, and we want it to be the cumulative distribution. So you'd be putting the word true here in that final argument. You would find then the probability of getting a value less than 0.505. Now, of course, the p-value is the probability of getting a chi-squared value more than 0.505. So that's why I've got this 1 minus at the front here, because we don't want this region to the left of 0.505. We want the region to the right of 0.505. So that's why we need to go 1 minus chi-squared dot dist, and we sub all that stuff in. Now, unfortunately, you can't use tables to get the exact p-value, so you're going to have to rely on Excel to get the p-value for you. You can find a range of p-values using the tables we just saw, but this is the only way to get an exact value. So if you plugged all that in, you'd get a p-value of 0.477. So that's the area that the shaded region represents, which we're not surprised by. 0.477 makes a bit of sense. It's very high. And again, we could construct the same conclusion. Do not reject the null hypothesis as the p-value is greater than 0.05. And we'd have the same conclusion. Okay, so there you have your chi-squared goodness of fit test. Now, here is the fun bit. If you found all that fairly straightforward, let me ask you this question. We know that the chi-squared distribution is derived like this. This comes from the previous video I've done on chi-squared distributions. It's a sum of a bunch of standard normal values. So the chi-squared distribution comes from the normal distribution. So this leads me to ponder, and I do like a ponder, especially while I'm eating a golden gay time. It makes me wonder, wait, where was the normal distribution in everything we just did? You're telling me that the chi-squared distribution comes from a normal distribution, but we didn't see any normal distributions, right? So this bit's going to get a little bit advanced, and if you're just happy doing the chi-squared goodness of fit tests without this particular piece of knowledge, then that's fine. You can skip through to the second example I do in this video. Or, if you're a little bit hardcore, stay with me because I'm going to try to explain where the normal distribution was in all that stuff that we just did. So if we go back to the original question, it says that 75 students are in the class and we're expecting 12% of them. So the proportion here, I've called that pi. The population proportion is expected to be 0.12. And x, which is the number of left-handed students in the class, is 11. Now here's my question to you. What distribution is it? How is x distributed? Well, believe it or not, it's actually distributed like a binomial distribution. Why? Well, this is actually categorical data. You only have left-handed students and right-handed students. So each person is either a yes or a no. And we have 75 of those yeses or nos. In other words, that is a perfect example of a binomial distribution. So x is just an outcome from a binomial distribution. Okay. What else do we know about binomial distributions, in particular when n gets pretty big? Well, this is where a lot of the concepts of statistics are going to come together. But if you've used a binomial distribution before, you may have seen something like this, where we can find a value z, which is x minus n pi. Now, your textbook might use a different phrasing of this. They might use p for pi, or alternatively, they might actually do this with the proportion of left-handed people, not the number of left-handed people, x. Either way, you can find a normally distributed variable z by subtracting the expected value from what we got, which was x, and then dividing by the standard deviation. Now, this is a normal distribution only because what's called the central limit theorem applies. Look, I'm throwing so much at you here, but as I said, if you really wanted to know where it came from, you kind of have to deal with a lot of these concepts. So because of the central limit theorem, we know that when n gets pretty big, as it is here, 75 is sufficiently large, this z value is going to be distributed normally. Now I've said here as n pi is greater than 5 and n 1 minus pi is greater than 5, and I've just basically shown you the criteria for the central limit theorem, which you might actually recall from the first part of this video. Remember how I said that all the expected values need to be greater than 5? Well, it's for this exact reason. It's for the reason that the central limit theorem needs to apply such that the underlying distribution is normal. So that tells you that, yes, this will be normally distributed, or at least effectively normally distributed. Okay. So what happens if we square it? Now remember that the distribution of z squared is actually going to be chi-squared. That's actually the definition of a chi-squared distribution with 1 degree of freedom. But can this equation be simplified? Hopefully you can see where this is going. When we square all this stuff, the square root on the bottom disappears. That's quite nice. We also have x minus n pi all squared. Now there's a bit of algebra to go here, which I'll happily put a link to in the description of the video if you really care. But you can get from this equation to this one quite neatly. And what this really is on the left here we have the number of left-handed people minus the expected number of left-handed people, all squared, divided by the expected number of left-handed people. On the right we have the number of right-handed people, n minus x, n is 75, minus 11. So that's the number of right-handed people minus the expected number of right-handed people, all squared, divided by the expected number of right-handed people. Does that look familiar to you? The observed minus the expected all squared divided by the expected. And you sum them all together. Isn't that interesting? So that's how we get this formula here, the sum of the observed minus the expected all squared divided by the expected. And we sum that for each particular outcome that we come across. In this case, there's only 2, left-handed and right-handed. Anyway, diversion over. I know there was a lot of statistical stuff in there, but for those of you that cared, that is why this is a chi-squared distributed statistic. So that's pretty full on, isn't it? But nonetheless, we can use this very simple formula thanks to all that work that was done. All right, so here's a quick additional example of a goodness of fit test. We're going to expand it just a little bit so that we've got 3 categories. It's probably a good opportunity for you to have a go yourself as well. So at the right time, I'll get you to pause the video, but let's read the question first. It says, out of 600 throws in a scissors, paper, rock competition, there were 235 rocks, 194 scissors, and 171 papers thrown. Now, the question I have for you is there evidence of a weapon preference at the 5% level of significance? Do people choose one of these weapons in preference to some of the others? Now, the first thing you're going to need to do is put together your table with the observed and the expected frequencies. And if you think you're up to it, pause the video here and have a go at putting together a complete and formal goodness of fit test. But I'm going to rip straight into it and go through it quite quickly to finish up this video. The null hypothesis is that the 3 proportions are equal. The proportion of rock throws is equal to the proportion of paper throws and scissor throws. And the alternate hypothesis, what we're trying to seek evidence for, is that at least one of those pairs are different. So the level of significance is 0.05. Our test statistic is a chi-squared stat, and it's only a chi-squared stat because the expected frequencies are all above 5, don't forget. So you'd need to state that somewhere if you're doing it officially. It's a chi-squared stat with 2 degrees of freedom. Why? Because there are 3 categories. K minus 1 degrees of freedom, so that gives us 2 degrees of freedom. The calculated chi-squared stat is 10.51 if you sub everything in correctly. And then the critical value that you get if you're using Excel, you could use that same formula we used before, except with 2 degrees of freedom. the critical value is 5.99. So our conclusion here is to reject the null hypothesis as the chi-squared calculated value is greater than 5.99. So we can say there's enough evidence here to suggest that a weapon preference does exist, and it seems that people prefer to throw rocks than they do scissors or papers. So that was really quick, but I just wanted to give you another example, one where there were more categories instead of just the basic 2 categories. And I hope you found this video informative and you're now confident in using the chi-squared goodness of fit test. The next logical video along would be the chi-squared test for independence, which should be the recommended video following this one. But even if you don't watch that, thank you for watching. My name's Justin Zeltzer. If you want to like and subscribe and do all that stuff, that'd be fantastic. I've got all the videos up on zstatistics.com. And hey, shoot me a line. It's nice to hear from my viewers whether the stuff I'm doing is helpful or whether there are things you'd want me to put up. So I'll catch you around.